I am Joseph Regi, and I am an artificial intelligence and high-performance computing consultant. You see my website, and the information is in there how to get in touch with me. So today I'm going to talk about protein structure prediction for drug development, and I'll focus on AlphaFold 3 primarily. So I'll talk about a workflow of artificial intelligence and high-performance computing tools for drug development, focusing in particular on AlphaFold 3, and I'll provide demo codes for the Performer and diffusion module of AlphaFold 3. I'll also talk about a little bit about RosettaFold, especially for protein design applications, and then references and conclusions. So this is what, in my mind, is an integrated drug design flow. Integrated means that it integrates AI and high-performance computing tools, and essentially from a purely calculation perspective. So we have the protein structure prediction using either AlphaFold or RosettaFold. This delivers a static snapshot of the protein in 3 dimensions. However, in reality, proteins have conformation changes in femtoseconds time scale. In order to be useful for drug development, one needs to predict the behavior in milliseconds time scales. So in order to bridge this gap, we have statistical and ensemble models, which are in this reference number 3. By the way, on the left side, you have URLs for the white papers for more information. An additional element is molecular modeling, which is from high-performance computing, and the task is to predict how drugs bind to proteins, how molecules bind to proteins using approximated solution of the quantum mechanic equations. In particular, if you look at reference 4, you will find deep learning approach in order to simplify, to approximate the quantum mechanic equations, giving good accuracy with considerable speed gain in terms of computation. Reinforcement learning is also an important item, and I'd like to call out here this work done by Argonne National Lab to optimize the plan, implement, and evaluate sequence at the experimental level. And finally, isomorphic AI is working on, together with Google DeepMind, on protein design. So this is the high-level architecture design overview of AlphaFold 3. And the task is to predict the 3-dimensional structures of protein, ligand, DNA, RNA complexes. So in that, it expands and amplifies beyond AlphaFold 2. The input to the model is sequences of proteins, ligands, covalent bonds, and it is augmented using template search and genetic search. These are from databases like Protein Data Bank, to look for similar structures. This is done using hidden Markov models. The conformal generation is applied on amino acid or residues by doing a lookup search in databases like Protein Data Bank, and they are calculated using experimental data-based calculation methods for ligands. The purpose of this module is to provide a feasible three-dimensional structure at the amino acid level or the ligand level. These data are going into an embedder. So you have here single representations and pair representations of tokens, and I'm going to speak about more in detail about this. The main computation block of AlphaFold 3 is called the representation learning, or the trunk. It includes template modules, so the templates that have been retrieved at the beginning of the pipeline are now further utilized, and similarly the multiple sequence alignment module is used and to update the embeddings, and also it is further updated in itself. That leads to the performer module, which is the main computation, and that is intended to ensure attention level based triangle-based consistency. So the output of each of these paths during the forward pass is fed into as input. This is called recycling, and it has some advantages over traditional machine learning methods. The final step, once we have all the tensors updated from the preceding phases, is to predict the three-dimensional structure of our complex using diffusion, a conditional diffusion algorithm. So in the diffusion process, you access the module using random noise, and upon conditioning with the tensors that have been updated at each time step, we progressively calculate the three-dimensional structure of the complex. In particular, I would like to call out the fact that in this phase, we apply random rotation and translation to assure equivariance of the process. So in terms of representations and embeddings, here we see a real-world example, which is a complex HSA ibuprofen complex. So the HSA protein is in green, and the ligand ibuprofen is in purple, binding with this protein. And here you see the sequence describing the complex. So we talk about the token level and atom level representation for the tokenizations. So tokens level are for standard tokens like standard amino acids and standard nucleotides. But for ligands and modified amino acids, we apply an atom level of representation. So, and also we have single representation and pair representation. The single representation at the token level is a tensor with the dimension n tokens by c. So this is the number of, these are the tokens in our sequence, and the vertical dimension is the features. The pair representation is n tokens by n tokens times c, where c is the channels, the features for that apply to each pair of tokens, let's say Zij. And a similar construct applies at the atom level, giving the Q tensor for the single representation and the P tensor for the pair representation. So you have these features that come from Protein Data Bank and other databases. At this stage, we have standard conformer for residues. So these are plausible three-dimensional structures for the amino acid or residues, and are retrieved from databases, whereas for ligands, they are calculated. So S is obtained from Q by linear transformations. The pair representations are computed from single representations, and we have this atom transformer which applies a tension mechanism in order to enrich, to improve the Q tensor. So to give you some intuition, the Q tensor goes through an attention layer where there is a bias from the pair representation, meaning that in order to determine how atom I pays attention to J, we include a bias term from the pair representation P, where this information is already encoded. The next phase in the model is the representation learning, also called the trunk. And here on the top left, you see the MSA multiple sequence alignment structure, which is, as you see, is a two-dimensional array. The rows are species, and the columns are positions, amino acid position within that species. And this representation and this array captures the co-evolution across species. So the key idea is that structure influences function of a protein. So if there is a change, like shown here by the blue and yellow boxes in specific amino acid, this is suggesting that these two amino acids are in close proximity. So that delivers a bias, an input on the structure prediction. The Buddha says evolutionary patterns in sequences, and how this is used. This tensor M for the multiple sequence alignment is used to update our pair level, pair level token representation Z. And how this is done, we have this tensor M, which is projected into tensors A and B. A and B are then used, columns of A and B are used to build an outer product, giving these two-dimensional matrices, which are then averaged and flattened, so that the end result is enriching the pair representation. The templates, which are similar structures retrieved from databases, are also processed in order to update Z. And there is a counterpart in this algorithm. We have row-wise self-attention on Z to update the tensor M. So leading to the performer, which is the main stage that I would like to focus on in this presentation. The purpose of performer is to refine the Z tensor and S tensor at the token level for the pair representation and single representation. And it does this job by ensuring geometric consistency for accurate three-dimensional predictions inspired by triangle inequality. So in a triangle, any side must be less, the size of the side of a triangle must be less than the sum of the other two triangles. So this is a way to drive the attention mechanism. And specifically, you will see there are two modules, triangle update and triangle attention, where, you know, tensors Z of ij pays attention to a third tokens k. There are also bidirectional effects because not all parameters are like distances, so there are directional dependent parameters among the features. So we are talking about outgoing edges and incoming edges. So in outgoing edges, we have this Zij pair and the influence of I to token k and j to token k. Conversely, in incoming edges is the reverse view where, again, starting from Zij, how token k pays attention to I and j. So this is the triangle update module, whose job is to augment, to enrich the token level pair representation Z, as you see here from input and output, and is obtained using linear projections and matrix operations between these projections A and B upon using a gating function, which then delivers an updated version of Z. And I'll show that in a demo program that simplifies the construct. The next step is triangle attention. Again, the purpose of this module is to enrich the pair representation Z. You do that using classical attention mechanism. So from Z, obtain projections to obtain the query, the keys, and the values. For Zij, this is at the row I of Zij, and the bias term is on row J, which is projected here. So the attention mechanism is calculated as usual. What is new here is the bias term and the gating term that resembles a little bit the LSTM model type. So the slide shows one attention head, and multiple attention heads are computed, concatenated to deliver a final update on the scene. So in order to explain this a little bit better, I've developed performer demo programs, which are used for education purposes, and they simplify the implementation, so they are non-learning, because in my demos the weights are constant, And also I have only one attention head and some other simplifications. So the first part is the triangle update. And the title of the slide takes you to the URL. The URL is the GitHub repo with the code. So I told you that Z is projected in two tensors A and B. And in this case, you see row 0 of Zij. So this is the tensor A, and row 1, which is in B. And so the second dimensions across the columns, index by index K. In this case, you see K equals 2 and how this contributes to the updating of 0, 1, so row 0, J equals 1. And in order to obtain the complete contribution from all columns, you have this summation formula upon applying the gating term, which I said before, mentioned before. And the slide also mentions other simplifications compared to AlphaFold. So the other thing is triangle attention. And so again, we start with the tensor Z for the token pair representation and project Z to obtain query keys and values. So we start with Zij with the appropriate weight matrix. For the keys and values, we use row I equals 1, and the slides, for the keys and values, we use row I, and the slide shows the specific case for I equals 0. And the bias term is for row J, which in this case, in the slide is J equals 1. So you build the attention mechanism in a classical way and compute the attention score as a dot product of query times keys plus the bias term. The result is passed into a softmax module, which computes the weight to be multiplied by the values in order to deliver the update on tensor Z. The third part of the AlphaFold 3 model is about diffusion, and the task of diffusion is to predict the three-dimensional structure of our complex. Upon conditioning, so the conditioning is based on the tensors that have been computed so far and are still updated during this process. The input is Gaussian noise, and the output is three-dimensional coordinates of each atom in the complex. So the diagram on the right is a little bit complicated, and it consists of 4 steps listed on the left side. These are intended to process the conditioning tensors in order to obtain at the end the three-dimensional structure. So the first step 1, is token level preparation. So we go in with the token level pair representation Z, as well as the single representation S, which were computed before. These are augmented Z. The token level pair representation is augmented with the positioning encoder, and the single representation is augmented with the time step embedding. This is at the token level. So we want to be more granular. So the next step is atom level. So we start with the initial embedding of our atom representation. And we take into account the pair representation to update C the initial single representation to deliver an updated version of the single atom level representation. At this point, we include the coordinates of the atoms, the three-dimensional coordinates that are computed in this particular time step to deliver an updated Q, single atom representation. And we apply again the atom transformer at this stage. Finally, in this stage, we project the Q to token level to deliver the A tensor. And the A tensor is used in the next phase using another attention layer with pair bias, using the bias from the token level pair representation Z, delivering an updated A, which then is used to update Q, the atom single representation, which is then used for the predicting denoising step in order to deliver the three-dimensional coordinates. So in order to explain this process, I've developed a demo which is intended to denoise a sine wave. And here you can compare, the slide compares the AlphaFold algorithm and the demo. So in the AlphaFold, we have multi-level transformers. In the demo, it's a simple multi-level perceptron. The conditioning in AlphaFold 3 is all the tensors that have been calculated in the trunk, whereas in the demo is just -1, +1 for invert or direct wave. In both cases, the input is Gaussian noise. In AlphaFold 3, we have position encoder and time step embedding. These are ignored in the demo. And the output of the demo is direct and inverted sine wave. So this is the structure, the demo architecture. You have here on the left the training side, and on the right the sampling or inference part. So at training, we generate training data, going to diffusion, add noise, which gradually add random noise to our structure, and going to a model to do condition denoising upon this condition of ±1. And the job of this module is to predict the noise that has been added at each time step. So it minimizes the mean square error, and by using that, it computes the gradients to update the weights. So when you do the sampling or inference, you start with pure random noise. You go through a diffusion, you go through a denoising step, a denoising function, which has, in this case, 1,000 denoising steps upon condition in order to remove the noise at each time step and come up with a result. So this is what it looks like after 2,000 epochs. We start with a clean sine wave, and we want to predict the same wave and also the invert wave in orange. And in the middle of the diagram, you see the result after 2,000 epochs. Besides AlphaFold, I would like to call out Rosetta Fold, especially for protein design. So Rosetta Fold evolved from ab initio methods, which are highlighted here on the left, to a deep learning model comparable to AlphaFold on the right. So the ab initio means that the proteins have been designed to perform a specific, the conformation of a protein has been obtained by physical methods like energy minimization. And here you see an example where an amyloid is captured by an ad hoc design of a protein. It goes through a number of iterations, and these are also evaluated experimentally until you come up with a viable product. So this is has been used for a long time by the David Baker's lab. So it's proven technology. However, it's very much time consuming in terms of compute resources. So they developed Rosetta Fold, which is based on deep learning. And here you see the high-level structure of Rosetta Fold, which also takes MSA, so including the query sequence plus similar sequences, and also two-dimensional structures from templates and three-dimensional coordinates from similar templates. The module, the compute module, is consisting of three tracks. 1D track where you have attention mechanism on the MSA sequences. Two-dimensional track applied on the two-dimensional template data, and the three-dimensional track using graph transformers. And here you have communications across these three layers. The equivariance is enforced by this SE3 transformer, which then delivers the final complex structure. This has been trained on Protein Data Bank and UniRef 50 models. And I like to call out the fact that this is also faster than AlphaFold. So it's for monomers, you can do that on a single GPU. And finally, some references. The first reference is the white paper I've been using all along, Illustrated AlphaFold 3. The second bullet is my own write-up, providing more details than I have presented today. And also, I would like to call out reference number 12, which is Protein Language Model. These are simpler models. They do not use MSA, and they support faster prediction of three-dimensional structures. They are not as accurate as AlphaFold, but it could be useful for less demanding applications. And reference 13 is from Google DeepMind. It has all the algorithms for AlphaFold 3. So I've presented, in conclusion, an integrated stack, integrated in the sense that it's AI and HPC, making many assumptions like knowing what druggable targets are and other practical facts that have been neglected. So it's a theoretical framework. In this perspective, AlphaFold is a game changer for precision. Ever since AlphaFold 2, they provide precisions that are comparable to state-of-the-art experimental results. It is flexible because it does not only proteins, but also ligands, DNA and RNA, and it is therefore an enabler for drug development. To explain a little bit better how it works inside, especially the performer and diffusion, I've developed this, sample, this demo codes. Rosetta Fold is a complementary technology and it's very interesting, especially for protein design. And the protein language model could be an interesting option if you are restricted in terms of compute resources. Thank you for your attention.